Hello everyone and welcome to the online lecture for Math 837. This is week 11 and lecture 1. The topic for today is integral test. Let's start with a recap. So we started talking about a series, and the definition of series was a series is a formal sum. A series from k equals 0 to infinity of ak is the sum of the terms in the sequence ak, right? And then we defined the partial sums. So the definition, the nth partial sum for the series k equals 0. Of course, the k equals 0, k equals 1, it doesn't matter where the series starts. Series ak is the sum of the first n entries. So in this case, since I'm starting at 0, I would go a0 plus a1 plus a2 all the way up to an. From here, we're able to define what it means for a series to converge to L. So definition, a series converges to L, or I'll just write it like k equals 0 to infinity equals L if the limit of the sequence Sn, as n goes to infinity, equals L. And again, we know how to deal with sequences. We know what it means for a sequence to converge to a limit L. And we use that definition to define what it means for a series to converge or add up to L. From here, we can use the definition to show a series converges or diverges. Sorry, I spelled it wrong. To show series converge or diverge using the following steps. So first, we compute Sn in a closed form, right, with an expression of some sort. And then 2, we take the limit. We take the limit of Sn. Now, the problem is this first step can be tricky in a lot of situations. And many series don't have a nice closed form formula for Sn, or it may be very difficult to compute. So which is why last time we also talked about the divergence test, which was a nice test to show if a series diverges. Today we'll be talking about our first convergence test, which is called the integral test. Integral test. Now the idea behind the integral test is we want to relate the improper integral of f of x dx from 1 to infinity. We want to relate that, the convergence of that, to the series ak from k equals 1 to infinity, where ak is equal to f of k. So is there a relationship between convergence? Now we know that the integral we constructed, so you make this right here. We constructed the integral to define areas under a curve. So now the question is, how do we define, or how do we interpret series as an area? How to interpret as an area. So let me demonstrate with an example. And the example is, Let's consider the function f of x equals 1 over x. And then of course the series will be the series from k equals, let's say 1 to infinity of f of k, which is the same as saying the series 1 over k. So this is roughly what the curve f of x equals 1 over x looks like. And we know the area under the curve, under a red curve, is equal to the integral from 1 to infinity of 1 over x dx. Now the series 1 over k from k equals 1 to infinity, I can think of this as 1 over k times 1, because if I multiply 1 by something, it doesn't change the value. And the way I interpret this as an area is I think of it as the sum of the area of rectangles, like a Riemann sum, where the 1 is the width and the 1 over k is the height. So now if I plot this out on the graph, the first rectangle has a height of 1 over 1, which is just 1, and a width of 1, so it would look like this. And the second rectangle would have the height of 1 over 2, and again a width of 1, and the third one will have a height 1/3, and then 1/4, and then so on and so forth. So the series is really just the area under the blue curve, or the blue staircase. Now in this example, we note that the blue area, or the area represented by the series, is strictly greater than the area represented by the curve, which is the red area. But note that if instead we start the series at k equals 2, so I have the same series but starting at k equals 2 of 1 over k, again times 1 just for the sake of example, the first rectangle will now have a height of 1/2. So if I plot this out, it'll start here. And the second one will have a height of 1/3, and the third one will have a height 1/4, and so on. Sorry, technical glitch. But then we know that this is equal to, this series starting at k equals 2 is equal to the green area, and the green area is strictly less than the area under the red curve. Now from the last lecture, we know that a series converges if and only if its tail converges. So we know that the blue area and the green area are finite. The blue area is finite if the green area is finite, and the green area is finite if the blue area is finite. And since the red area is wedged between the blue area and the green area, we can say that the red area is finite if and only if the blue area is finite, and the blue area is finite if and only if the red area is finite. And that is essentially what the integral test is. It says that the integral of f of x from 1 to infinity converges if and only if the corresponding series also converge. So let me write that down formally. So theorem. And this is of course the integral test. Integral test. I'll let f be a continuous, non-negative, so 0 or greater, continuous, non-negative, and decreasing function. And let ak equal f of k, then the series ak from k equals 1 to infinity, and the integral f of x dx from 1 to infinity, they either both converge, or they both diverge. both diverge. And we've spent time learning about improper integrals and determining when they converge and when they diverge. So now we can use all those skills to determine if a series converges or diverges. Now, one thing to note is this only works for f that are continuous, non-negative, and decreasing. And they have to be non-negative, decreasing on the interval 1 through infinity. Okay, so let me start by giving a formal proof of this theorem. And the formal proof is essentially going to be just the picture we drew earlier. So first I'm going to do the proof. So I'm going to start by assuming that the series converges. So assume the series AK converges. And I'm going to define a new function g. Define g of x as follows. So between x equals n and x equals n plus 1, g of x is going to be f of n. So essentially, if I go back to the drawing, g of x is just the blue curve, or the blue function. And this is, of course, for all integers, so n is an integer. And now observe that the integral of g of x from 1 to some integer n, again, going back to the diagram, is just the sum of those rectangles up to n. So it will simply be equal to the sum of f of n times 1 from n equals 1 all the way up to, I should use a different variable here. K equals 1 to n. F of k. And this is just equal to the series k equals 1 to ak up to n. And this last thing we know is just the partial sum Sn. So now if I take the limit of both sides of this equation, I get that the limit as n goes to infinity of the integral from 1 to n of gx dx, and there should be a dx up here as well, dx is equal to the limit as n goes to infinity of Sn. And we know that the series AK converges. Let's say it converges to L. Then this limit as n goes to infinity of Sn is equal to L. But also the limit as n goes to infinity of the integral from 1 to n is just equal to the improper integral from 1 to infinity of gx dx. So we know that the improper integral of g of x converges, and it converges to L. Okay, next, we know that f is increasing. So f of x, is decreasing, which means that f of x is less than or equal to f of n for all x greater than n. And in particular, this implies that f of x is less than or equal to g of x for all x, because g of x is just f of n between n and n plus 1. And again, to see this, it's just a matter, looking at the diagram, we can see that the blue curve is greater than the red curve, and the red curve represents f of x, and the blue one represents g of x. And from there, we also have that f is non-negative. So because f is non-negative, we have that 0 is less than or equal to f of x, which is less than or equal to g of x. And if you recall from a few weeks ago when we talked about the comparison test for improper integrals, we can use this fact to say that the improper integral from 1 to infinity of f of x converges because the integral from 1 to infinity of g of x converges. And this was by the comparison test. Which we covered a few weeks ago. Comparison test. So therefore, we have done one side of this theorem. So therefore, the series ak k equals 1 to infinity, where ak equals f of k, converges. F of k converges implies that the improper integral of f of x from 1 to infinity converges. Okay, now for the other direction, assume that the improper integral of f of x dx converges. Just like before, we're going to define a new function. Let's call it h of x. So define h of x equal to f of n between n minus 1 and n. And this is for n integers and n greater than or equal to 2. And actually in the last one, it should have been n greater than or equal to 1 as well, but... Right. So if you go back to the diagram again, here h of x just represents the green curve here, or the green staircase, whatever you want to call it. And just like before, we're going to say, we're going to observe that the integral from 1 to infinity of h of x, or sorry, 1 to n of h of x dx is equal to the series that starts at k equals 2 of f of k all the way up to n. And again, we saw this in the diagram that we drew, where the first all the rectangles are just shifted over one. So we start at k equals 2. And just like before, we're going to take the limit to get the improper integral. So the improper integral of f of x, or h of x dx is equal to the limit as n goes to infinity of the integral from 1 to n of h of x dx, which is equal to the series starting at k equals 2 to n of f of k. Sorry. And again, because f is increasing, or sorry, it's decreasing. Because f is decreasing, f of x is greater than or equal to f of n for all x less than n, which again implies that h of x is less than or equal to f of x for all x. And again, f of x being positive implies that h of x is positive. So we have that 0 is less than or equal to h of x, which is less than or equal to f of x. And again, by the comparison test, this implies that the integral of h of x from 1 to infinity converges, because we assumed that the integral of f of x dx from 1 to infinity converges by the comparison test once more. And of course, the integral from 1 to infinity of h of x, we just said was equal to the series starting at k equals 2 of ak, which is again, it says equal to f of k, to infinity. So this series converges. And this implies that the whole series converges. So this implies that k equals 1 to infinity of ak converges by a theorem we did last time, which I called the tail of series theorem, by the tail of series theorem. And that shows this, the second or the other direction for the theorem. So now let's get straight into some examples. And the first example I want to start with is the series 1 over k from k equals 1 to infinity. So last time, in the last lecture, at the end of the last lecture, I said that this series diverges, and I gave a very hand-wavy argument. Let's show that this diverges more formally. So by the integral test, the series diverges if and only if the integral of 1 over x dx from 1 to infinity diverges. So all we need to do is compute the integral, the improper integral. And in case you've forgotten, the way we do this is by setting it as a limit from a goes to infinity, from 1 to a, 1 over x dx, which is equal to the limit as a goes to infinity of ln of a, which is equal to infinity. So therefore this diverges, the integral diverges, so 1 over diverges, and implies that the series diverges. And this is a much more rigorous proof than the one I gave last time. Now more generally, we can look at the series 1 over k to the power of p, k equals 1 to infinity. And again, we're going to use the integral test, so we're going to consider the integral 1 over x to the power of p dx from 1 to infinity. And we covered this this improper integral in a lot more detail a few weeks ago, so I won't get into it again, but if you recall that this integral, it converges if, so converges if p is greater than 1, and it diverges if p is less than or equal to 1. So that implies that the corresponding series converges if p is greater than 1, and it diverges if p is less than or equal to 1. And this series here is called the p series, and it's it's very important type of series, so I'm going to write this actually as a theorem. So theorem convergence and divergence of p series. So 1, the series 1 over k to the power of p to infinity converges if p is greater than 1, and 2, the series diverges if p is less than or equal to 1. And of course the proof of this we just did using the integral test. Diverges if p is less than or equal to 1. And of course the p equals 1 case is just the series that we covered in the last example, which is the series 1 over k. This is a very important type of series. It has a name. We're going to call it the harmonic series. So that's how we use the integral test to show convergence or divergence of p-series. Now let's get into some other more general examples. So example, let's consider the series k e to the minus k squared, k equals 1 to infinity. Again, we're going to consider the integral test here, so consider the improper integral. So we replace all the k's with x's, so x e to the minus x squared dx from 1 to infinity. We write this as a limit, so limit as a goes to infinity of the integral 1 to a of x e to the minus x squared dx. And hopefully at this point you know how to solve this this integral. It's just equal to a limit as a goes to infinity of e to the minus x squared times minus 1/2 evaluated at 1 to a, which is equal to the limit as a goes to infinity of minus 1/2 e to the minus a squared plus 1/2 e. And as a goes to infinity, the first term just goes to 0, so this is equal to 1/2 e. So this improper integral does converge. It converges to 1/2 e, which implies by integral test that our series, our series converges. E to the minus k squared converges. One thing to note is this doesn't tell us what it converges to. It just tells us that it converges to a finite value. But to actually determine what the value is, we have to use other methods. And this is of course coming from the fact that if we go back to the picture, the blue area, the red area, and the green area, we've shown that if one of them is finite, then they're all finite, or rather, there's a relationship between the red one being finite and the blue one or the green one being finite, but that does not imply that they're equal. And in fact, in this picture, we clearly see that they're not equal, which is why the integral test is only useful to show whether a series converges or diverges, but it's not actually used for determining what the series converges or diverges to. Okay, and I'm going to end things there. Thank you for watching. Today we learned how to use the techniques we learned about integrals and improper integrals to determine if series converge or diverge. Next time we'll continue to develop more tests to see if series converge or diverge using other methods. Hello again everyone. There's a small correction that I wanted to make regarding my examples. I'm realizing this one day after I finished recording the video, and there's no way for me to go back and change the middle of the video, so I'm just going to add it to the end. And the correction is, if I go back to the original theorem, let f be a continuous non-negative and decreasing function. That's the hypothesis, that is the condition of the theorem, and I did not check that in my examples. And it's very important that when we use a theorem that we check that the conditions for the theorem are met. So in this case, f of x is equal to 1 over x, which is of course greater than or equal to 0 for all x greater than or equal to 1. Or let me instead write this as x in the interval 1 through to infinity. And now we check it's decreasing, and we do that by saying, well, if x is greater than y, then 1 over x is less than y, 1 over y, which implies that f of x is less than f of y. So this part here, we have that f is continuous, we have that it's non-negative, and we have that it's decreasing. Therefore, we can use the theorem about the integral test to say that this series diverges by the integral test. Okay, and then similarly in this example, here f of x is equal to 1 over x to the p, which again is continuous and in x between 1 and infinity, and continuous and positive, and also it's increasing, the same reason as before. If x is greater than y, sorry, not increasing, it's decreasing. If x is greater than y, that implies that x to the p is greater than y to the p, which implies that 1 over x to the p is less than 1 over y to the p. So again, it's continuous, it's greater than or equal to 0, and it's decreasing. Therefore, we can use the theorem to say that it converges. Oh, sorry, this got erased. If p is greater than 1, and it diverges if p is less than or equal to 1. And finally, with my last example, same thing. So again, we have that f of x is equal to x e to the minus x squared, which is greater than or equal to 0 and continuous on x in 1 through infinity. And it's greater than or equal to 0 because both x and e to the minus x squared is positive. Therefore, their product must be positive. And to check that it's decreasing, we simply take the derivative. So the derivative of this, if we apply the product rule, we'll get 1 minus 2x times e to the minus x squared. And note that if x is greater than 1, then 1 minus 2x is negative, and e to the minus x squared is always positive. Therefore, the derivative is less than 0 for x in 1 through infinity. And that implies it's decreasing. So again, we have that f is continuous, it's positive, or it's non-negative, as greater than or equal to 0, and its derivative is negative, therefore it's decreasing on the interval x between 1 and infinity. And because of this, we can again use the integral test to conclude, as I've done here, that this series converges. It's very important that we check the conditions. If on a test setting you don't check the conditions, you will lose at least partial marks for your solution. And that covers the correction. Thank you for watching, and I'll see you next time.